All right, so as Brian mentioned, my name is Jeremy Fairbank. If you're interested in following me, I'm El Papapoyo on Twitter and J Fairbank on GitHub. So this talk is called Solving the Boolean Identity Crisis. And really our goal today is to analyze the ways we have used Booleans in our code base and think about some of the downsides that they can actually bring. And then we'll discuss how we can harness awesome Elm features to be able to overcome some of these issues with Booleans to write clearer code for not only ourselves, but also for our team. Very briefly about me, I work for TestDouble as a remote software developer and consultant, and we believe that software is broken and we're here to fix it. So our mission is to improve how the world builds software. And we like to do that by not only working alongside your team to help you get stuff done, but more importantly, to help your team improve and grow. So if you're interested in learning more about how we can help your team grow, or if you're interested in joining an awesome team of developers, please say hi at testdouble.com. And as Brian mentioned, one more quick thing. I'm actually writing a book on Elm with the pragmatic programmers, and the book's been in heavy development for a while now, so hopefully it's going to be in beta soon. If you're interested in learning more, make sure to follow me on Twitter as El Papapoyo for future updates. So I actually want to start off by talking about Redux. That is, I want to talk about a common theme I saw arise in how I was approaching state in Redux. It's relevant because it led me down an unmaintainable path to building state that I brought with me to Elm. So as common these days with front-end development, I was building applications that depended on data from a server. Now, actually retrieving and sending the data wasn't really the problem I want to address. Rather, the difficulty I ran into is how to deal with a lot of the meta-client state that's related to fetching the data. So let's use this as an example, an application that fetches a dog from a server. Let's say we're building a rescue adoption application. So the first important piece of state we need is to actually have a dog. Initially, we don't have anything. We're in JavaScript, so we'll just use a null for that. So this object then represents this implicit initial ready state. Now we need to fetch the dog from the server, but we should provide some feedback in the UI to our users. The view layer is driven by state in Redux, very similar to Elm, and so we need to add some additional state to our previous object to represent that we are fetching some data. So Booleans are cheap in JavaScript, so let's add a new Boolean property called fetching. When it's true, we can display a spinner to our users. Otherwise, when it's false, we'll assume we're in that implicit ready state, waiting to fetch a dog. But wait, the fetching property should also be false when we actually have our dog from the server. Now our state needs some way to represent the fact that we've successfully retrieved our dog. Okay, well we could add another Boolean property called success. When it's true, then we should have our dog. Otherwise, if it's false and fetching is false, then we're in our ready state. Oh, but hold on. What about errors? The server call could fail, or we could run into authorization issues or any other host of problems. We need some way of knowing we have an error so we can relay that to our users. Fine, let's add another Boolean property called error, as well as a string error message property. If error is true, then we'll display the error message. If it's false, then we have to start weighing the other Boolean properties to decide what our current state really is. More importantly, what do we do when we have state that looks like this? All three Boolean fields are true. So what current state are we really in? We're going to have to ensure that our Redux reducer can only produce valid states. That means we're going to need lots of additional testing. When we operate on this state, it doesn't really reflect what is that valid state either. We have to use if-else branching with arbitrary ordering where some Boolean properties rank over others. This just adds additional complexity and it really is a weak safeguard for dealing with the possibility of invalid state. We're prone to display the wrong thing to a user if we're not careful. So what's the ultimate problem here? Well, I thought these properties were separate concepts that were totally unrelated to one another. Instead, they are intrinsically interconnected. They are a set of states where you can really only be in one of them at a time. So I had multiple pieces representing one thing. That makes it harder to reason about the overall state of my application. And it makes it especially difficult to continue maintaining that if-else complexity and the need for precise reducer functions and tests. This was a rampant pattern that I kept using for a while and unfortunately brought over to Elm when I first started using it. I was unfortunately embracing something called primitive obsession. So primitive obsession is this act of using primitive data types like booleans, strings, and integers to represent domain concepts. Examples of this might be using floats for currency or strings for like a status field in a record. In my applications, I had some domain concept of remote state. I was either waiting to fetch, fetching, had successfully retrieved that state, or had encountered an error while fetching that data. So representing that single domain concept with multiple Boolean values led to extra code complexity and confusion about how to check which state I'm in. I bring up this example I encountered because it highlights an interesting dilemma with Booleans. Booleans are a core primitive data type in almost every programming language. We use them everywhere, whether that's in state, in function parameters, or even return values. But do they really provide value to us as programmers, especially in high-level programming languages? Booleans necessarily create complexity with branching logic in our code, which can violate principles like single responsibility. Booleans also pull us away from friendly domain abstractions in our code like we saw earlier with the primitive obsession. Robert Harper, who is a professor at Carnegie Mellon, has a blog post on something called Boolean blindness. And in that post, he offers this insightful quote about Booleans. There is no information carried by a Boolean beyond its value, and that's the rub. So what Robert is saying here is that Booleans really don't tell us much. They lack context about their usage. We as programmers, we have to intimately know the code base to understand what Booleans are representing. Put another way, a Boolean is really just a binary data type with no inherent meaning. It's just true or false, on or off, 1 or 0. We as programmers attach meaning to Booleans, but they are just simple values that are agnostic about how they are used. Kind of like the presence or absence of electrons in a light bulb. It has no ideas that it's producing light for us. But really, what's the harm in using Booleans? Well, what's going on in this function call here? We have a book flight function that appears to be booking a flight to St. Louis. But what is that second argument of true really doing? It's just a value. It doesn't describe its meaning or purpose in this function call. It's up to us as programmers to figure it out in the code base and then keep the meaning of that argument in the back of our mind. We're offloading the abstraction to our memory instead of the computer. And if we add more Boolean arguments, we exacerbate the problem even further. Now we have an even more confusing function call. We'll need to dive deeper into the code base to understand what those Boolean arguments are doing. Add on top of that the mental gymnastics to remember what each value represents, as well as what the correct order of these arguments needs to be. So how have we arrived here? Booleans seem like such a fundamental concept that is important to math, logic, and computer science. So they seem like they are a natural fit in programming. Yet they go against a lot of software principles that encourage abstractions and code reuse. So let's take a step back in time when Boolean thinking really began to emerge. In 1847, George Boole developed this symbolic system of representing mathematical logic known as the Boolean algebra. Boole's goal was to organize logic more formally into this system to make logic more broadly approachable. So we think of algebra in terms of numbers, but Boole developed this system of algebra that could operate on truth values like true and false or 1 and 0. So this notation is the foundation for how we think of true and false as values that we can combine through operations like and, or, and not. Eventually, these ideas made their ways into computers and programming around the beginning to mid-20th century. An engineer, Claude Shannon, proved the equivalence between the Boolean algebra and electrical circuits to show that circuits could be used to solve the same problems that Boolean algebra could solve. So this led the way for the foundation of digital circuits that comprise computers. It's hard to tell what the original motivation really was for introducing Boolean values into languages. However, it's easy to see how programming's roots in math, logic, and circuits would have led language designers to bring these true and false values into languages as well. So why can that be a bad thing? Well, let's divert our attention briefly to logic in terms of this Boolean thinking. The Boolean algebra, recall, was constructed as this formulation of logic, so it fit very well there. Now, logic deals with concepts of proving statements to be true or false. And one of the best examples of this is propositional logic. So propositional logic is a branch of logic devoted to the study of propositions or statements. It is based on combining separate statements through logical connectives such as and, or, and than to create more complicated statements. Looking at our example here, we see that propositional logic consists of premises and conclusions. Each premise and conclusion is fundamentally a proposition as well. In propositional logic, we can take one premise, like if it's raining, then it's cloudy, and based on the logical connective then, we can take the next premise, that it's raining, and conclude that it's cloudy. So thinking back in terms of Booleans, we can define a proposition like so. A proposition is a statement that expresses a concept that can be true or false. So it makes sense to adopt a system like Boolean algebra as a way of transforming these propositions into a formal notation. The danger in that, though, is that it opens up the door to conflating Boolean values with propositions. A proposition that is true is something we can prove to be true. It doesn't mean that the proposition is equal to true. What I mean is that a proposition is an assertion and a Boolean is a data value. All that to say that conflating Booleans and assertions in logic is fine. The values true and false have some meaning in terms of logic and proofs. But in programming, it can make code less understandable. When we reduce properties of our code, things that are true about it in terms of its business domain, to just Boolean values, we lose a lot. Specifically, we lose the intent of that code. What does this Boolean argument to this function represent? What does this Boolean property in my state represent? We also lose information. In branching logic, we know something is true only inside of our if check. The body of an if-else expression immediately loses that information, meaning it can violate the property that we just checked to be true or false. And we'll look at that in more depth when we talk about the concept called Boolean blindness a little later. So let's start to solve this problem of losing intent and information. We will walk through 4 key areas where this Boolean thinking affects the code we write and the applications we develop. More importantly, we will see how this can negatively impact our teammates. Through this process, we will see how some of the features we already know and love about Elm will easily allow us to solve this Boolean identity crisis. So let's return back to our book flight function. Imagine coming back to this part of the code base after a few months. It'll be hard to tell what this function call really does because of that Boolean argument. This problem highlights that loss of intent I mentioned earlier. We have lost what this argument means by relegating it to a Boolean value. Now we're forced to look up the definition of this function to understand it. So we go to this function and we see that the Boolean represents whether the customer is a premium customer or not. So we can store that in the back of our mind and then continue using the function, right? But what about the else branch? We'll have to assume that maybe it represents a regular customer, or it could represent something else. Also, what if our system needs to support multiple types of customers in the future? Here's another example from a UI perspective. We're constructing an opacity slider and a volume slider by partially applying this view slider function with a Boolean. Again, we can't tell definitely from this function call what this argument does. So we again visit the definition and see that the Boolean represents whether this slider is horizontal or not. In the else branch, though, we end up with some implicit state. Here, implicitly, this is a vertical slider. So it's not only confusing what this argument does from its usage, but we're again encapsulating binary state with meaningless values. There's no way for a caller to know what the implicit state is without reading through the code. So Boolean arguments create this loss of intent. Uncle Bob offers an additional opinion on the downside of using Boolean arguments. Boolean arguments loudly declare that the function does more than one thing. They are confusing and should be eliminated. So we saw from previous examples that functions typically, they may have multiple responsibilities because of branching. And when you see a Boolean argument, you know the function definition will likely have an if-else expression. So let's look at this further and see some other examples where these Booleans can be a little problematic. So Boolean arguments can also be misleading as to their intent in relation to other functions. So here's an adapted example from a story by Uncle Bob that quote comes from. So in this story, a programmer is working with control rods at a nuclear power plant and needs to rotate these rods by a certain amount. Without looking up the definition of rotate control rod, this programmer assumes that the arguments are the same as an earlier example that uses rotate fuel rod. So based on what rotate fuel rod looks like, we can assume that it rotates the fuel rod by 30 degrees when the second argument is true. It's perfect. This programmer needs to rotate the control rods by 30 degrees. So they make a similar call to rotate control rod, passing in 30 and true. To this programmer's dismay, though, the control rods end up rotating too far, over 270 degrees too far to be exact. So this gross overcalculation could be catastrophic, especially when dealing with nuclear power plants. So what happened? To figure out this problem, the programmer finally visits the definition and discovers the problem immediately. For some reason, these functions were not defined the same. Rotate fuel rod's Boolean argument determines whether the angle is in degrees when it's true. But rotate control rod's Boolean argument determines whether the angle is in radians when it is true. So not only do we have a loss of intent in each individual function, but the function calls can mislead us in the future because their Boolean arguments aren't consistent in their usage. Finally, let's return back to this example. Based on what we've discussed so far, what happens when we have multiple Boolean arguments? Take the previous problems we've discussed and now magnify that issue. These 3 Boolean arguments add lots of more complexity, creating really confusing code. So these functions also can violate the single responsibility principle, causing them to do more than they should. Now you might say, so what? Like I definitely did in the past. I wrote the function, I understand how it works, and I can always go back to relearn it. It's worth the simplicity. But what about the rest of our team or future code maintainers? I had to begin to think really hard about this. Even with my context within these code bases, I would still have to look up what these Boolean arguments were doing. Imagine how my teammates might have felt. They would need lots of more time to ramp up to understand the code base and see what's going on. So, when it comes to writing APIs, Martin Fowler offers this advice. An API should be written to make it easier for the caller. So if we know where the caller is coming from, we should design the API with that information in mind. Now, this quote is more geared toward the caller being another piece of code, but I think it's also very fitting to think of it in terms of our teammates and future code maintainers. So I know it's cliche, but I really think it's always worth repeating. We're really writing code for humans more than we are writing code for computers. We should strive to make our code understandable and approachable for our teammates and those future maintainers. That shows a greater level of compassion and care for others because we want our team to succeed, and we want them to succeed as individuals as well. So we've talked about a ton of problems with Booleans. How can we begin to solve this dilemma for us as well as for our teammates? Well, a first good step might be we could, say, replace the Boolean variable with something at least a little more self-documenting. We could try strings initially. Now, when we see a call to book flight, we have a lot better idea about what that second argument is doing. It relates to a customer type. In the function definition, we can handle this pretty easily with pattern matching. So we can match on static strings just like this and explicitly show that we're handling premium and regular customers. Note that we also have to handle every other string with this wildcard match. That might indicate that maybe we can improve this even further. So one problem with using strings here is that it is still primitive obsession. Any string value is valid here. So we have to handle invalid values or values that are out of our business domain. We do that with that wildcard match that we had in our case expression. So we need something better to represent our domain of valid values. How do we typically represent a finite domain within Elm? And ideally, it should eliminate the need for runtime checking of valid values too. This is where union types come to the rescue. So instead of using strings, we can create a union type called customer type with the values premium and regular. We can call book flight in a self-documenting way, but use our customer type values instead. And of course, we can continue to use pattern matching with these new values. And the perk with pattern matching and this union type is that now we get the compiler reinforcement. We can only handle valid constructors for our type, and if we leave one out, our application won't compile. We can take a similar approach with our rotate functions. We can create this angle union type with two constructors, degrees and radians. And then each constructor can wrap over a primitive angle amount as a float. So instead of functions that are confusing in their relative usage of a Boolean, we can explicitly specify the angle amount with the correct angle unit. So we can make it more convenient for our callers. Again, inside these functions, we can use pattern matching on that angle. Now, more than likely, these rods have similar shapes, meaning this code might be a little duplicated. So we can refactor a little further even. We could reduce this down maybe to one function that just expects a rod, whether it's a fuel or a control rod. And we can use maybe extensible records or a union type for those rods if needed. And so we have a nicer function that is easier to understand and call. Now, something else we could consider, though, is that we technically still have branching here, which might seem at odds with Uncle Bob's earlier advice on branching. Our branching has simply changed from an if-else to a case expression. So another idea is we could separate the functions out and potentially eliminate the need for the union type. So now we have distinct functions, rotate in degrees and rotate in radians. So that's another approach where we can make it more convenient. Now, one little downside that I'll mention is that this can still encourage primitive obsession, and it might just be a subjective preference, but I still prefer using more of the union type approach, mainly because union types can help better encapsulate domain values for us in our applications. Regardless, we could even have the best of both worlds. So we can keep our single rotate function that takes an angle, and when we branch, we can instead delegate responsibility to the more primitive rotate in degrees and rotate in radian functions. So that way, rotate is more of a collaborator and avoids making the function have multiple responsibilities when branching. Regardless, the key takeaway here is that we want to make APIs understandable and convenient. We want it to be easy for our teammates and even ourselves months later to easily comprehend and approach our code base. So far, we've talked about functions that accept Boolean arguments. But what about functions that return Boolean values? Could we also run into issues with this? So to introduce this concept, I want to share an anecdote from Dan Licata, a professor at Wesleyan University. He says, sometimes when I'm walking down the street, someone will ask me, do you know what time it is? If I feel like being a literalist, I'll say yes. Then they roll their eyes and say, okay, well, tell me what time it is. The downside of this is that they might get used to demanding the time and start demanding it of people who don't even know it. It's better to ask, do you know what time it is? And if so, please tell me. That's what time is it usually means. This way you get the information you were after when it's available. So if we were to translate Dan's tale into code, it might look something like this. We have a do you know the time function that returns true or false. We can call it and branch on the result with an if-else expression. If it's true, then we can call the tell me the time function. Otherwise, does anybody really know what time it is? So the problem with this code is that the compiler may not know that the property that the person has the time holds true. Therefore, there's nothing stopping us from accidentally demanding the time from a person that may not have it. The compiler may not prevent this depending on how we've implemented these functions. So we're at the mercy of runtime branching being correct. This creates a problem known as Boolean blindness. When you reduce information to a Boolean, you're prone to lose that information easily. The information that Boolean carries is only known inside that if check. As soon as you branch into the body of the if-else expression, you're now blinded to the original information that got you there. Because that Boolean loses information, you have to backtrack to recover that information when you need it again. Connor McBride, a lecturer, provides this insight into the problem of Boolean blindness. To make use of a Boolean, you have to know its provenance so that you can know what it means. All right, what is he talking about there, and what's up with this fancy provenance word? Now, this isn't Providence, Rhode Island, where you can pick up organic homegrown Booleans. Rather, provenance refers to the birth or origin of something. When we branch on a Boolean, we're mostly trusting ourselves to write code that is valid given the value of that Boolean. So when we get in gnarly, nested branching, we can lose track of what is what and need to search back to the beginning of our branches to recover that lost information. Not only are we blinded to that information like this, but so is the compiler, as I mentioned earlier. So what are examples of this problem? Well, let's take a JavaScript example that finds a dog by name. We take a name string and an object of dogs. When we branch to see if the dog exists in the object, we immediately lose that information. We're trusting ourselves to write this correctly, and there's nothing stopping us from attempting to retrieve the dog in the else branch, even though it doesn't exist. If we wrote the equivalent code in Elm, we have the same problem, although it's kind of a silly way of writing this function. We again take a name string, and in this case a dictionary of dogs by name. Then we check if the dog exists with the dict.member function, and we branch. But the Elm compiler, it doesn't retain that information and know that it's safe to directly access the dog. Instead, when we use dict.get to retrieve the dog, the safety of Elm is going to force us to essentially do the same check. If the dog is available, then it'll be wrapped inside just. Otherwise, we'll get back nothing. Here's another classic example with division. Let's say we want to avoid dividing by 0. So for our division result function, we will use a helper function called canDivide. Again, when we branch on canDivide to perform division, we immediately lose that information that the denominator was 0. So we could still attempt to perform division here in the else branch, and nothing would stop us. How can we approach this problem of Boolean blindness and try to avoid these functions that return Booleans? So Dan Licata also offers this advice. Boolean tests let you look, options let you see. What Dan is saying is that when we branch on a Boolean, we're only testing for a property. We still need to do additional work to get the information we ultimately need. An option lets us perform the test and see what information we ultimately needed in the first place. So what does Dan mean by an option? And how can we start returning that instead of Booleans so we can make our code less cumbersome for us and our team, as well as leveraging the Elm compiler to safeguard us? Well, why not use maybe? In fact, the option that Dan refers to is the option type in ML languages, which is also known as the maybe type in Elm. So with our find dog by name function, we were already getting maybe back from dict.get, so we could remove our unnecessary if-else expression. By returning maybe, dict.get lets us test and see the information we were after. Does the dog exist, and can I have it? And now the Elm compiler ensures that only the just branch can access the dog. We can't accidentally access it in the nothing branch because the compiler knows it doesn't exist at that point. So we can apply this same idea of returning maybe with our time analogy. We can write a new what time is it function that takes a person and returns the time if it's available inside a maybe type. This prevents that problem that Dan proposed earlier of demanding time from people that might not have it. We could even go a step further and introduce a custom type to provide additional reasons why we may not have the time. Here we have a till time union type with 4 values. If we have the time, then we'll wrap it in a time constructor. Otherwise, we'll let the person know why we don't have the time, such as no watch, no phone, or no sundial. Finally, we can apply this idea with our division example. Instead of testing for division and then allowing it, which could fail, we could create a custom division function that handles the division and returns a result. Therefore, we just attempt division inside division result and access a valid result inside of an OK. Otherwise, we can provide reasons why division couldn't be performed in an error. Now, the divide function still suffers from the Boolean problem because we're dealing with a primitive operation when we look for 0. We necessarily have to do that equality check in the pattern match. But the main goal is to minimize the extent of this Boolean branching. So we can unit test this function really well, and then the rest of our code base can use this safer divide function to access a division result. So ultimately, the point is to harness union types to give us powerful abstractions for writing clearer code. Instead of only testing with Booleans and then losing information, we can see with union types. This simplifies APIs for our callers. It also requires less code and testing because the compiler can enforce these constraints thanks to type checks. So now let's return back to our application state, our third key area. We have our same example from the beginning of fetching a dog, but now implemented in Elm. We already identified the problems this primitive obsession creates in the Redux example with the 3 Boolean properties. That still applies here in Elm. Recall that we will have lots of branching complexity with this arbitrary ordering of these Boolean properties. Add on top of that the issue of Boolean blindness that we just discussed. There's no guarantee that just because the success property is true, that I'll actually have a dog now. So really, we're prone to still display incorrect information to our users. Additionally, there's nothing preventing us from not handling a particular case, like errors. So the compiler is not going to ensure that I'm taking care of things I leave out because it's blind to the states my application can really be in. Another big problem is that invalid states are still possible, such as all the Boolean properties being true. Which state are we really in here? Keeping this state correct will require more unit testing to prevent the bugs from invalid state. So building an application around this type of model creates unnecessary complexity and headache for you and your teammates to test it and then decipher and understand what the proper order of these fields needs to be. So this is a common hurdle, at least for me, for adopting Elm and rethinking how to represent state. In fact, Richard Feldman, I'm not sure if you've heard of him, seems like he's kind of a big deal, talked a lot about this at last year's ElmConf. So Richard shares that many invalid state problems can actually be solved by just how we represent that state to begin with. Essentially, we want our representation to prevent invalid states from even being possible to begin with. So recall, we identified 4 disjoint states that sort of make up what is the overall state of our remote dog. Since we are really in only one state at a time, why can't we fix our model to enforce this through the compiler? We can use union types to accomplish this too. So union types can work like a finite state machine where we represent each possible state of fetching a remote dog inside a union type called remote doggo. We can take each Boolean property and the implicit ready state to create the values for our union type. We have ready, fetching, success, and error. Notice that the success constructor wraps a dog type, and the error constructor wraps a string error message. Then inside our model, we can create a dog field that uses our remote doggo type. That means our dog can only be in 4 valid states, and there is no chance of mixing up fields into an invalid state anymore. So not only do we eliminate impossible states, but we make the code clearer for ourselves and our teammates with stronger domain concepts. Inside our view function, we can swap our if-else branches for case branches. Now there is no doubt about being in a correct state, so we don't have to worry about the order we match each value, and we don't have to worry about displaying wrong information to our users. We also don't have any loss of information with Boolean blindness. We test and we see the information we need through the success and error constructors. And even better, if we happen to not handle a particular state in our application, like the error case, well, the compiler is going to catch that through exhaustive pattern matching on the union type, ensuring that we handle all the possible states of our remote doggo. So this is such a common paradigm with fetching remote data in Elm that there's actually already a library for doing most of this. So there's this remote data package from Chris Jenkins that offers this reusable union type called remote data. And the remote data union type is just like our remote doggo type, but with a couple differences. So some of the constructors are named a little differently, but they still map one-to-one. Not asked maps to ready, loading maps to fetching, failure maps to error, and success stays the same. Also notice that there are now two type variables, E and A. This lets you use whatever inner error and successful type you need for your application. So you can fetch something besides dogs, and you don't have to worry about writing a whole nother union type. Now, outside of fetching data, this concept behind using union types to represent separate states is incredibly useful. For example, take a to-do type that has separate Boolean flags like is complete or is editing, or maybe a customer type with several account types, platinum, gold, and silver, but they're all Booleans. For each of these, we can just combine those Boolean fields into one union type. So for our to-do, we can create a to-do status union type with complete and editing constructors. Then the to-do record only needs a single status field for these two possible values. Similarly, with the customer's account type, we can create a union type called account type with three constructors, platinum, gold, and silver. So the customer record then just has one account type field that can be one of those three values. So union types are really like the superhero of Elm. We can eliminate so many of the problems with Booleans and better represent our domain by consolidating separate fields into one state representation. Impossible state becomes impossible. More importantly for our team, code becomes more understandable and manageable. Now we could conclude with that, but I think there's one more area where we could analyze the problems with Boolean thinking and devise maybe a better solution. So far we've been discussing a lot about the importance of writing clear code and replacing problematic Boolean code with union types. And our main focus has been really on improving APIs for ourselves and our teammates. But what about our users? Can issues with Boolean thinking create problems for the users of our applications too? Yes, it can happen very easily in our UIs if we're not careful. Take, for example, one of the most notorious form controls, the checkbox. When the user checks the checkbox, they know that at some point this form will save some information to an archive. If the user doesn't check the box, though, what's the alternative? Our user might be wondering if the information will be saved somewhere else, not at all, or if maybe a modal is going to appear and prompt them to save it somewhere else. So this checkbox suffers from Boolean thinking. It's essentially just flipping a bit, where we know the possibility when it's true, but not so much when it's false or unchecked. We as programmers might know what the meaning behind that checkbox is when it's true or false, but that's really unknown to our users. So this type of UI and UX violates what Jeff Atwood calls the don't make me think rule. And it comes from a book called Don't Make Me Think by Steve Krug. And in his book, Krug describes common sense approaches to developing usable websites. And the idea is to make our UIs and our user experiences as intuitive and helpful as possible. You don't want to force your users to think harder or guess what their actions might do on your site or application. That can lead to a lot of user frustration and a loss in your user base. So we should approach our UIs with our users in mind. We already learned about the importance of designing APIs for callers, especially in making them more usable and friendly for our teammates. Why shouldn't we do the same thing with our UIs for our users? So another great book that helps us approach our interfaces from the viewpoint of our users is The Humane Interface by Jeff Raskin. This book offers a ton of suggestions for improving interfaces by having developers consider the design of their interfaces with users in mind. And I really love the title of this book because it uses the word humane instead of just the word human. If you look up humane in the dictionary, you get this definition: having or showing compassion or benevolence. I think we've all been in a position where we're frustrated by user complaints about the software we build. But what if some of their complaints are valid because we've poorly interpreted or dictated how they should interact with software? I know I'm guilty of this. So instead, we should adopt a humane mindset and think how we build our UIs with our users' best interests in mind. So returning back to our Boolean checkbox, how can we begin to make it less confusing for our users? Why not treat it similar to union types? We can encapsulate all possible states with radio buttons instead. Then the user clearly knows what the possible options are and what the ramifications of selecting one option over another are. But could our users maybe still have a little difficulty even with this? What if a user is worried by the use of the verb save? Will it save when they click on one of the options or after they submit the form? So with verbs, users may not know whether the action has taken place or is yet to come. How can we prove this? So Jeff Raskin suggests another thing here that says we could go a step further and use adjectives instead of verbs in labels. In this way, we describe the state of the object after it's submitted. And this should hopefully alleviate some of our users' concerns over when the saving is going to take place. Now, depending on your situation, you might need a slightly different approach, but the point is to look at your UI from the perspective of your users in order to make more humane interfaces. So test things out and see if it's making positive impacts in user engagement and satisfaction. So we've spent a lot of time pointing out a lot of the downsides of Booleans. We saw that Boolean arguments make code confusing for us and our teammates, and they can add complexity to code. Returning Boolean values led to problems like Boolean blindness and opens the doors for bugs. Spreading the state out among Boolean fields led to invalid state and required more complexity in testing to prevent bugs. Even Boolean thinking and UI can create frustrating user experiences for our users with just a simple checkbox. So is it time to sunset the Boolean and say goodbye? I actually don't think so. I think we need a healthy balance for when Booleans do and don't make sense. We still need to compare numbers, check equality, and filter lists, which all require Booleans. And really, this talk was never just about deriding Booleans, because they can have a place. Boolean binary thinking is still a critical foundation of computing and really will always have a place in certain situations. Really, this talk is about one thing, and that's empathy. So as developers, we're not islands. Whether we have teammates or not, our code may meet future maintainers. It's easy to write code that we ourselves understand and we're willing to maintain, but we can grow so much more when we place ourselves in others' shoes. And I don't mean just grow in our technical abilities, like some of the techniques we saw today, but grow as compassionate humans, because I think that is what is so important. By growing in empathy, we become more selfless and caring of others. That ensures that not only our teams succeed, but that others succeed, which hopefully leads to a better world for all of us. So thank you so much for listening today. I really appreciate your attention and hope you all grow as more compassionate developers.